If you are diving into Solana development, you're going to hear a lot about accounts, PDAs, and CPIs. But what do these terms actually mean? In this video, I'll explain the core concepts that power Solana programs, from how data is stored to how programs talk to each other. In the second part, we'll get hands-on and build a simple program that lets user deposit and withdraw SOL using a program-controlled account. But before we write any code, let's understand how Solana works under the hood. Unlike Ethereum, where a smart contract can hold its own state internally, Solana takes a very different approach. Everything is an account. There are a few types of accounts you will work with in Solana. Program accounts, these store executable code, and data accounts. These are used to store program state. You might also hear about system accounts. These refer to accounts owned by the system program, one of Solana's built-in native programs. It's responsible for creating new accounts, and by default, any new account, like a wallet, is owned by the system program. Every account has a fixed amount of space and can store both LAM ports, Solana's native token, and arbitrary data. But here's the key thing. Programs do not own state internally. Instead, they read and write to accounts that are passed to them. To interact with any data, you must explicitly pass in the accounts your program will use. Now, how do we trigger a program to do something? With a transaction. A transaction is a container that holds one or more instructions. An instruction tells a specific program, hey, run this function and use these accounts. For example, if you are transferring tokens, your instruction might call the SPL token program and pass in the source, destination, and account. Solana is fast and scalable because multiple instructions can be packed into a single transaction, and even run in parallel if they don't touch the same accounts. Programs on Solana are usually written in Rust and deployed to the blockchain. By default, they are upgradable. Each program has an upgrade authority, an entity that can redeploy new code to the same program address, known as the program ID. If the upgrade authority is removed, the program becomes immutable and can no longer be changed. Once deployed, a program lives on-chain as an account that stores executable code. It just sits there, waiting to be called via instructions sent from transactions. Here's something important. Programs can't sign transactions. Even though the program ID is derived from a key pair, the private key isn't used and can't be used at runtime. Programs don't have access to private keys at all. So if your program needs to control an account, it can't use a traditional wallet. That's exactly why we use something called a program derived address, or PDA. A PDA is a special kind of Solana address that is derived from a set of seeds and a program ID. What makes it special? It has no private key. It can only be signed by the program that created it, and it allows a program to control an account without needing external credentials. Think of it as a secure vault your program can access, but no one else can. You will see PDAs used everywhere to store NFT metadata, user profiles, escrow accounts, anything a program needs to own and manage. Now, here's where things get powerful and a bit more advanced. A cross-program invocation, or CPI, lets one program call another. For example, let's say your program needs to transfer SOL. It can't do it directly because it doesn't have permission to modify LAM ports on wallet accounts. Wallet accounts are owned by the system program, and only the system program can change their balances. So if your program wants to transfer SOL, it must make a CPI to the system program, asking it to perform the transfer on your behalf. This same idea applies to other on-chain programs. You can call the SPL token program to mint or transfer tokens, or even your own second program. Every account on Solana is owned by a program, and only that program can modify its data or LAM ports. So a CPI is like calling another program's function and asking it to do something for you. To make a CPI, you provide the program ID of the program that you want to call, the accounts that program needs, the instruction data, which includes the function you want to run, and any arguments. This follows the same format as building a client-side instruction. CPIs are powerful, but they require precision. You need to pass in all the required accounts and sign properly if you're using a PDA. Alright, that was a lot, but now you should have a solid mental model of how Solana works. Accounts store everything. Transactions execute instructions. Programs are stateless and need PDAs to control data. And CPIs let programs talk to each other. In the next part, we will get our hands dirty and we will build a simple CRUD application using Solana and the Solana ecosystem. Let's dive deep into the code.
Let's start the demo, and for this one we will use Anchor. Anchor in Solana is a framework that simplifies the process of writing, deploying and interacting with smart contracts. Think of it like what Hard Hat or Truffle is to Ethereum, but tailored for Solana with some extra features. And of course, it uses Rust, and we will also write some TypeScript code. To create a new project, we type Anchor init and then the name of the application. We will call it CRUD simple. We'll create a simple CRUD application for Solana. Once it's done, we step into the directory and then we open this with any IDE you want. In this case, I'll use VS Code. As you can see, we already have some folders and files. I want to bring attention to this programs folder that has a CRUD simple folder inside that, and then src lib.rs. And here we basically have a hello world. We'll replace this code with something a bit more complicated. And also I want to reopen VS Code using WSL, Windows Subsystem for Linux. Okay, let's replace this code. And we have a declare ID. You can use a placeholder for now. We'll replace this with a real ID later. Then we have a couple of constants, max username len and user profile space. We'll have a module called CRUD simple. All the functions in the program module represent the program's instructions. Use a super, and then we have different functions. Each function requires a context where T is a struct annotated with derived accounts that defines the accounts required by the instruction. The first one is to create the profile, and then we get the context, the username, and then we return a result. And we have a profile with an owner, username, age, and bump. We have some fields useful to create a profile. We also have a simple log on line 20. Another function to update an existing profile. In this case, we need the profile and then, for example, username and age if we want to update that. The structure is very similar. We also have a similar log. Another function to delete a profile. In this case, we just need the context to delete the profile. And we'll return a log with the key of the profile deleted. This is not enough. We need some structs for these functions. So we need a struct to create a profile with different fields. Each field in the derived accounts structs represents an account required by the instruction. And the type of each field in the derived accounts struct functions as a security check. The account passed by a client to a program is the expected type. The account attributes within the struct function as constraints that define more checks on the accounts for functionality. For example, init means the account will be created. Payer is the account paying for the account creation. Space is the number of bytes to allocate to the new account, and so on. A struct to update a profile. A struct to delete the profile, and you also need a struct for the user profile and one to handle errors. For example, if the username is too long or if it's unauthorized. Now we could test this with a simple anchor test command, which starts a local validator, builds and deploys, runs test, stops local validator, and so on. But in this case I want to do things manually because I want to show the step-by-step process to test this application. So we will write a simple TypeScript file, and then we'll write anchor build and anchor deploy manually. So let's create this demo.ts file in a folder called scripts. Let's write some TypeScript code. I'll go quick here because this is just for demo purposes. We have some imports, also web3.js, and then we have an async function to run this demo. We can leave a simple log, a couple of variables for the provider and wallet setup. We'll do this on the local system, cluster URL and connection. Then a wallet path that of course it will need to be updated. And then we define a wallet key pair with a try catch in case we find some errors. We also define this variable to load the program. It also returns an error if it fails to load the workspace. Derive PDA, which stands for Program Derived Address. It's a special type of address that a Solana program, also called a smart contract, can own and control without needing a private key. And then some instructions. One to create the profile. This is just for demo purposes. All the code will be available on GitHub, no worries. One to read. In this case, we just fetch the program account user profile. One to update an existing profile, update the username and update age, for example. Then I want to read again. We're basically testing what we wrote in the lib.rs file. And I also want to try to delete a profile here. So we are testing the functions in the other file. Let's verify that an account has been deleted. We also leave a log demo finished, and then we run the demo. We also leave a console error in case the script fails. Okay, that was quick. Again, you could also use just anchor test, but I want to do things manually here. Okay, now it's time to test this application. Let's type anchor build. This might take a while, the first time that we run this command. And once anchor builds this project, we will also have a real ID that we can use here at line 4. Okay, let's find this ID. And for example, we can find it in this anchor.toml file. Let's replace the placeholder. We start an npm project. We install some dependencies, for example, TypeScript. And now we can type Solana test validator. Okay, great. It's up and running. Now on a different terminal, leave the other one open. We can type this command Solana airdrop 2 with these options just to check if it's connected. As you can see here, we have a good output. As you can see here, we have a correct output. This was just to test if everything is connected properly. And then the final test. We type anchor build again and anchor deploy. And this will deploy our application. This is amazing. It really simplifies the development process. And the final check is to run the script. So npx tsnode scripts demo.ts, the TypeScript file we just wrote a couple of minutes ago. And great, as you can see, it tested all the functionality in the lib.rs file, and we have a proper output, also with different usernames. We also updated the username, we deleted one, so everything worked fine. All the code will be available on GitHub. This is an open source project, so feel free to open an issue, suggest some modifications, and also feel free to leave any comments in this video. If you want to know more, check the Solana documentation at solana.com/docs. For example, you can try a quick start to build your first Solana program directly in the browser. This is the end of this video. I hope that this was clear. I really wish you best of luck if you want to become a Solana developer.